So let's continue. So now let's go over to the more technical part, how actually images are formed. And typically you have an image formation process where you have some kind of excitation that goes through a sample that produces a response, and finally this response is captured by a detector. Could be, for example, just a light, a lamp that goes through some semi-transparent material, and then you see how much comes through. Or maybe it's reflected. So then we're talking about microscopy, for example. Could also be higher energetic radiation, for example, X-rays, which actually go through many more materials, more dense materials. And again, you get some kind of shadow that is captured by the detector. Another way would be that you emit some microwaves and see reflections in the material, which is then captured by a detector, which is an antenna in that case. So it could be really very different kinds of information that go through. And how they interact depends also on the physics of the source and how that kind of radiation interacts with the material. Then you have exactly the absorption, reflection, phase shift, scattering, emissions, whatever. And for that you have different kinds of detectors. Typically what we often do today is we use a camera type of detector, or maybe if you have then sound waves or magnetic fields, then you may need some kind of transducer to sense that. Oh, where am I now? Hello, here. So now it works. And here is a table of different sources. And myself, I'm mainly working within X-ray and neutron. I did also some microwaves, but these are the main techniques that I have been working with. And other ones more come in contact with in the hospital, like ultrasound or MRI, but then I wasn't actually doing the measurement myself. So there are quite many types of imaging modalities, and of course you need to choose the one that is relevant for your type of investigation. And each type of course also has its advantages and disadvantages, very characteristic artifacts that could happen too when you do it. And so in principle we have two ways how the images are obtained. One is through direct imaging, so the detector sees more or less exactly what you measured, and it's easy to directly see the output. So that is using a typical camera of the object to make images of the object. Then you get something like this. In this case it's just a bit blurred, it's upside down, but then with some reconstruction you can remove some of the blurring and also flip it in the right way. The indirect and computational imaging, then you measure in a different domain. That is, for example, when you do measurements in MRI, you essentially work in the frequency space, and then you need to do a inverse Fourier transform in order to get to the image object itself. Also in tachography, which is actually a diffraction method, then you see some diffraction spots, and out of these diffraction spots you can inverse the image and get a real space model of the information. And when you look at the traditional imaging, you have this light source, and then the information, if it's transmitted or if it's reflected, goes through a lens and then is projected on an image plane. And that can be more complicated written, as we have a sequence of convolutions of different interactions with the object. And we see here there are some transfer functions that do work on the sample and how the information, how the beam is walking through the space. Also detector transfer functions, and then on top of it you may have some noise information that is added from the camera. And for color images or multispectral imaging, then all of a sudden what you see is actually an integral over the wavelength, so the whole thing gets even more complicated. But so this is what's happening within the imaging process. And for the indirect computing is, for example, computer tomography, which is used a lot in both in medicine and also in material science. What you do is you acquire a lot of images around the object, and all these images are back projected into a virtual volume that represents a three-dimensional object. Another one would be to do light field photography, and through one measurement you can computationally play with the depth of field within this scene. So here you can see that first you look at the far field, and then afterwards you can look in the near field, and this is from a single acquisition. You can also work with diffraction patterns using hyperspectral imaging, for example with Raman measurements, or you can even do surface topology with atomic force microscope, where you have a cantilever that more or less follows the profile and draws an image about the elevations in the object. So finally we come to the images. And first of all, a very abstract description of an image is it's a pairing of some information. So you have a spatial information, and you also have some kind of intensity information. So every point has an intensity value, and you know where it is. And mostly what we are working with, at least here in this class, is 2- and 3-dimensional images. Occasionally I will also mention 4-dimensional, and that would be in the dynamic imaging case. Then we can come up in the 4th dimension. So what we have is usually x, y, and z coordinates on a grid, a matrix, and we have a numeric value, which is the intensity. This numeric value could, in some cases, be some kind of vector. So if you, for example, have a color picture, then you have 3 channels, RGB, and that would be that you have a vector on each position. The vector could even be longer, so in some kind, if you work on hyperspectral imaging, it could be that you have a whole spectrum behind each pixel. That's also something I'm going to talk about more in, I think, dynamic or in multimodal imaging lecture. So it's probably in April or May that I'm going to mention more about that. And when you go around in the world is continuous in space and time and intensity, everything. But the computer cannot handle that, so we have to discretize the images, so we get it into our grid. So we need to work on discrete levels and even limit the size of what we are measuring. And the 2 examples here, I have a continuous intensity, and it's spatially distributed. So we would have a very smooth image if it was continuous in space. But when we put it in the computer, all these levels, they have to be discretized on a certain number of levels. Typically, our cameras, they work with 8 bits or 16 bits. So 256 gray levels or 65,665 gray levels. Or in some cases, we're also working with the floating point, and then it's a little bit sliding, but still you have a certain number of discrete levels. So what does it mean to us? Here are some examples of the same object sampled in different ways. And I'm going to, on the following slides, going into this in more detail. So first of all, we want to talk about pixel size and resolution. These are words that are very often misused because of actually commercial reasons, because the camera and monitor manufacturers, they are talking about they have 4K resolution. That means they have 4,000 pixels, not a resolution in 4K. 4K resolution doesn't really exist in a physical sense. So what we have is a pixel size. Each pixel on the camera has a limited spatial dimension, and actually the pixel size decides the pitch between the step between each measurement point in the image. And it's also the smallest area that is represented in the image. When we're talking about resolution, it's actually a physical concept which tells about the optical ability to resolve some object. So it depends on the optical transfer function of the acquisition system, starting with maybe if you have an X-ray or neutron system, you have a scintillator that converts the radiation into visible light. Then you have a lens and you have a camera, and all together they give some degree of blurring. And typically the resolution, that's the opposite actually. I have to check that one. You need to have twice as many pixels because of the sampling theorem, so I need to change that one. So you need to have twice as many pixels as your resolution in order to be able to capture it. And of course, the resolution defines what is the smallest pixel size you can use. And looking at different pixel sizes, here I have the original image. It has something like 900-ish pixels on the horizontal axis. And I do a downsize. That means the pixels are 4 times larger, and by 2 by 2. And it still looks quite okay, almost the same, probably because the screen can't show it. But if I do a really tough downsizing, 32 by 32, you start see the very large boxy pixels in this image. So this is for the features you have in the image and what they can resolve. This is way undersampled. And looking at the resolution on the other side, if you have an ideal edge without any blurring, it's a very sharp step in the image. It goes from pixel 1 to pixel 2 and nothing. And also with the extra condition that you manage to match the edge exactly on the pixel column. In practice, we usually have some kind of smooth edge. So the gray levels, they have a gradient over several pixels, and that is what we actually see in many of our images. And depending on what you want to do, you may look into how you can improve your resolution in order to actually see what you want to see. Because if the blurring is hiding your objects, then there is no point in doing the measurement. The other sampling I talked about was the image intensity, and here I'm looking at I think this one was 16-bit, but maybe only 8. It doesn't matter because the eye cannot resolve it anyway. So for the visualization point of view, let's say it's 8-bit. That one I resampled into 16 levels, and it is okay, but you can start seeing that you have some plateaus, for example, around here, where it gradually goes down in a few steps. And then when I undersample the gray levels really tough, going down to 4 levels, then we can only see that we have a blob and maybe some variations in the background. And that's obviously not good enough. 16 levels, depending on the application, could be useful in this case, but it's usually best to have the raw data with as many levels as possible, and then do downsampling as you go. So how many bits are really needed for different applications? So if you look at different features, so first of all, what contrast differences have you in your image? And then how many different features do you want to differentiate within in the sample at different gray levels? And also the sensitivity to rounding errors, because the less gray levels you have, the more sensitive you are to rounding errors. So when you look at few bits, you usually have a very high contrast image with also with high signal to noise ratio, something I'm going to talk about in 2 weeks. You have clean images, and you could also use it for segmented data. So for example, if you have only 3-4 classes, of course, then you can work with 2-bit images and save a lot of data. Many bits is when you have low contrast in the images, if there is a considerable noise component, and also if you have gradual changes in the image. And finally, for floating point, it's also something that is used, and typically it is when you have very large dynamic changes within the image, then the floating point can capture that. And also if you want to do quantification of physical quantities. And finally, in algorithms, depending on the type of algorithm, it's also beneficial to work with a floating point in the image. Some algorithms that where people want to speed up things, they may even go down to 1-bit images, but that is for speeding up. Oh, floating point. There are different ways to represent data. You have integer numbers, which are described in bits, and then you have discrete steps. Say 8-bit, you have 256 gray levels, so 1, 2, 3, 4, up to 255. And in floating point, you represent real numbers. So it can be any number, rational, irrational, whatever. That can be represented in floating point. And technically, it has one part that describes the value part and one part that describes the exponent.
So when you're doing confocal imaging, I can select how many, like if I'm doing 8-bit or 16-bit.
Mm-hmm.
There is nothing I can do about the last part. Is it like
The floating point is, I would say, something you would use when you do the processing.
okay? So it's not an acquisition.
The acquisition is mostly, as you say, 8 or 16-bit.
Okay.
Some cameras do 14 or 12, but but in principle, the camera does integer values. Another tool or tool that we use, actually I use often as a first inspection of the image. So of course I look at the image, and then I compute the histogram of the image. And the histogram is a representation of all the gray levels present in the image. In this case, let's see, do I have that on the next slide? Yes, I do. In this case, you can even identify different regions, that the dark parts are not very high frequency, so you see they are represented here. The bright background has a very narrow high peak, and that peak tells us that there is not so much variation in this area, and there are very many pixels represented by this gray level. In this case, I normalized the data from 0.4 to 1.0, because otherwise it's only zeros outside. So this tells me a little bit about the variations, for one, and actually also about the noise levels, something we are going to look into a couple of weeks. And with that, I get also an idea how easy is it to separate different features in the image, which will be in 3 or 4 weeks that we look on that. But anyway, this is the first information, and to compute it using Python. So here is actually a piece of code. In principle, this is the important line, where you see that I have a histogram of the image, and I say I want to compute the histogram in 200 bins, which means I will have 200 points along this histogram, and in each point the gray level interval that matches is put into each bin. Sometimes you want less bins, sometimes you want more bins, but depends on the level of detail in the image and the gray level distributions. And usually, again, now that I show the code, just to point something out, usually I try to separate that the important part is separated from the visualization part. So mostly the last 3-4 lines of each example is just for the visualization, and it can be a bit messy, to be honest, to make things nice. So I'm trying also even to put a little comment here, visualization, and then you know this doesn't have to do with the example itself. And there is, however, useful information in it, because you can see how to plot things nicely. So if you want to learn how to do the plots, then there is learning material here. But for the object, or for the task I want to demonstrate, is usually the upper part of the cell. So we have some examples of histograms. So here I have a noisy bi-level image. You can see we have a lot of bright, then we have dark, and if you look really close, you can see that this one and this one are different gray levels. And if we look at the histogram, we can see that there is a big representation of the dark. And then there is some bumpiness in the histogram down here. And finally, there is a wide one for the noise in the background. Looking at a real image, so this is a neutron image of this camera. It's usually not so clean as the synthesized example, where we more or less have 2 main levels, but it's a gradient between different gray levels distributions. And depending on the type of images you have, it can be almost, well, it's not uniform, but very well distributed across the whole dynamics range. In some cases, much less. And a very special kind is if you have bivariate data, so you have data from 2 different sources. In this case, it's neutron and X-rays, which I'm working with. But it could, for example, in the hospital be X-ray and MRI, or ultrasound and MRI. I don't know how often they are used together, but I think X-ray and MRI are clearly, possibly X-ray and ultrasound. So there are different combinations of data. And then you can do pairwise generation of the histogram, and you can get a plot like this. And then you can, in some cases, more easily identify regions. This is what I'm going to do in the second but last lecture in May. So, visualizing gray levels. Again, we have the human eye that we have to work with. And 8 levels are usually easy to distinguish. 32 levels is on the limit, depends on the screen and on the surrounding light conditions and a lot of other things. But 32 levels is more or less the limit, and if you go up to 256 levels, it looks like a smooth gradient, and you cannot distinguish the differences. So then it's more like in more larger regions, this region is darker than that region, but you cannot really tell that is level this and that is level that. What you can do is to play with the brightness, for example. So you narrow down that you only look at a part of the dynamic range. So here you see in the histogram, here I'm focusing on the dark parts, and you can see those regions. And then you can shrink the gray level interval and help your eye to better interpret what is happening in that part. Same would be to look in the higher region here, but what we can see is only the boundaries, that there are some gray level changes in those, because those gray levels are only represented in these regions. But you can actually, with the help of this, you have a tool for helping you visualizing and finding relevant features. So that is useful in the initial analysis, when you're starting getting acquainted with your data, to know what you can do with the data. Then we have the contrast, where you can also select different parts, if it's wide or narrow. And with that, you can also again say, let's have a narrow one. Then you can focus on a very small interval of gray levels and put all the visualization into that region, or you can get a greater overview, like in this one. And looking at an image, it's typically an image, as I said, is a bucket of pixels. And we have the coordinates, x and y, and we have an intensity. And that can be represented as a table, but that actually doesn't really help us very much. So what we instead do is we view it as an image, and then you can see here each level. Here I even plotted the intensity value. That is a trick. Showing the intensity values is a trick that you essentially only can do when you have very few pixels, and if you zoom in a small region, because otherwise it would be very cluttered and you would only see the red from the numbers. So this is for few applications when you want to zoom in and have to see, for example, how well an algorithm is working in a narrow region. Then you can do it like this. And then, until now, we have mainly looked at gray level images, but as you know, we also have colors, and you can actually apply color maps also to gray level images, and sometimes it's helpful, sometimes it's misleading. And here are some examples of pseudo color maps which you can use. So here is one called Blues. That one I think is Jet, and that is Parallel or Viridis, depending on which toolbox you are, which language you are working with. Parallel is for MATLAB and Viridis is for Python. They give more or less the same color scale. And here I have a lot of different color maps, and some color maps are traditionally used more in different fields than others. One that I would like to point out in particular are these, which are kind of diverging. So if you have something that is circulating around a central value, you can use this kind of color maps to identify it's positive or negative. And each color map is looking at, here we look at the different color components. So in principle, what the color maps are doing, they are mapping a single gray level to 3 channels, RGB. And here you can see how these are distributed for the different colors. And let's see, yeah. So here we have my test image. This test image, by the way, is a piece of petrified wood, if you wonder what it was. Yeah, so this is what it could look like if we use the different color maps. And here is what you would do. You show the image like this, and then you tell which image color map name you want to use. And the names are, for example, in the list that I showed before. Each of these color maps have its particular name. The default one in Python is this one, and I think, meanwhile, also in MATLAB. I haven't been using MATLAB for a very long time, so I don't know what they are doing nowadays. Then there is also a different way of mapping. So here we just have the grayscale, one called hot. And in this case, it's a logarithmized grayscale. So that puts more emphasis on other regions. So that could also be a way to do the visualization. In images, we can do different operations. So let's start with the pixel-wise operations, which means you have 2 images of the same size, and you do operations taking the same pixel in both images and do something with them. So we have the arithmetics. We can also apply different functions. And on a more global sense, you can also look at statistic functions. So we can compute the mean intensity or standard deviation, minimum and maximum of images or image regions. And that can be used for preliminary measurements. So the basic comparison between 2 images that change just slightly is maybe to compute the mean value and see if there is a difference in the mean value. It's a blunt tool, but you could do it this way. And another one is to demonstrate the arithmetic functions. So an operation that we do a lot in imaging is a normalization, flat field correction. And here we in principle have the image and the illumination field without the object. And then we need to subtract the DC, which is the dark current, a bias that is introduced in the camera to better handle the thermal noise. And so here we have the sample image, the open beam or flat field, the dark. Here I show the dark as just black, but it's more or less a constant level with some sorry. With some slight noisy ripple on it. In some cases, you can see even that there are different ship segments in the dark current image. So then we apply this, and you can see that this image, which is unevenly illuminated, after the normalization, you have a flat background, and this is actually the information that we want to work with. 3D images, there are 2 ways of seeing 3D images. One is that you actually have a 3-dimensional volume, but also a time series, that is a movie, can be analyzed as a 3-dimensional image. which actually makes sense because then you can see better do tracking if you do filtering if you do it as a 3D instead of analyzing each frame in the movie. And here you can see one example that we have a dot here that is bumping up and down, and if you look at the frames themselves, you see that it's just moving a little bit. But if you would extract a slice in this direction instead, you will see how this dot is moving along a sine curve. And doing it a 3D image as an array would be that you use this package called NumPy and want to arrange and creating a shape which is three-dimensional, and then when you print this, it comes out like this. So you have the two-dimensional matrices and a stack of those. And that can be demonstrated with plotting as either trying to do the 3D rendering, which I'm not going to do here, but we could also do a mosaic or montage like this, where you can see all the slices put together in this way. 4D images is the next step up, and that would be that we actually have a movie of volumes. And I'm not going to talk very much about this during this course, but it's actually the step up that you do a time series of tomography and want to follow things in the fourth dimension. But typically that analysis is done in 3D, and then you see what happened between the steps of the 3D volumes. And as I mentioned, we can have multiple values per pixel. You can have intensity and transparency, for example, or actually, as I said before, a color image is actually also multiple value per pixel. And yeah, here's just an example of that, plotted out as dots. And oops, yeah, and here is a a combined. Let's see if I can do scrolling here. I can't. That was deactivated. Okay. Hey, come on. So, yeah. But anyway, down here you can see a little bit how intensity is giving the color, and transparency is used as disk size. So you can combine, show pairwise of data in this way, and by using more and more refined ways, you could make more complicated, but the need for explaining what you actually show increases as well. Yes?
Which kind of modality would you get transparency from?
I actually don't know. It was just something I grasped. You could, in principle, after some computational steps, you could compute it. I mean, no, that's too far away. You could get it through the normalization. With that, you would extract the transparency in a way. So you can computationally extract it, but I don't know really how I would measure it with a specific modality. Yeah, and then with hyperspectral imaging, here we have some a microscope image, and then on each of these points there would be a spectrum behind it that that would be measured and analyzed. And well, that's a quite time-consuming type of measurement. In our group, we have a collaboration where we do the tomographies, the easy part, and the colleagues, they do Raman spectroscopy on a lot of points, and then afterwards we want to match those two to do element mapping of the experiment. It's a very tedious way of measuring, but sometimes you get that kind of data too. And yeah, so there you would have, for example, wave number and intensity value as information in the plot. And that could look something like this. a bit messy to analyze, but from that you could do the higher dimensional analysis. But again, also that is something that I'm saving towards the later lectures. And just shortly, a little bit on workflows for image analysis. Thing is, when we work with a lot of data, it is actually a lot of image processing is ridiculously parallel. So every pixel is you apply the exact same operation, which means you can use all the cores you have available in your computer, or even if you go to a cluster, you could bring up different chunks and process them separately, and you would have a more or less linear speed up by number of cores when you do that. And yeah, the development is that clock speed may have stopped, but the number of transistors are steadily increasing. So that is the development that we can benefit from in our analysis. And well, different modalities. We don't even have to just use the CPU, but also the GPU is fantastic for doing this kind of processing with some overhead to get the data over to the GPU. But the important conclusion is that at some point it's very important to work with parallel code or selecting libraries that do it. It's not so, actually, it's also a kind of a trap that if you start doing parallel coding, you start spending your time doing that because it's not always so easy to do. So better check out if someone has already done parallel processing of your for your task, then by all means use it. And the other thing is computing power is expensive, and nowadays we have a lot of different available resources. Some here at ETH, we have our own clusters, but you can also buy in on different of these services. So for example, if you use Google Colab, then you can say, I'm buying, say, 10 CPUs and so many GPUs, and it costs you some money, but not as much as if you would buy a new workstation yourself and maintain it. So these are also possibilities to consider if you want to do this processing. Of course, there are a lot of things to think about, how you can get all your lot of data to these services, but that's something they also have considered with their storage capacity. Yeah, okay, I take this one too. So workflow analysis. This is, I like cooking. So let's make a simple soup, just as a recipe. What you need to do is you need to buy some carrots, peas and tomatoes at the market. You need to buy meat at the butcher's. And then when you come home, you have to chop the carrots, you have to chop the potatoes, heat the water, and wait until the water is boiling. And then when that's done, you can add the veggies and wait 5 minutes, and then you add the meat, and then you boil it until the meat is tender. Something like that. So this is a clear stepwise procedure, and also a way how we can work with it, our data. Say we do the acquisition, we do some filtering, we do some segmentation, and everyone nicely step by step through. Another way would be to describe the steps what you want to do, and having hold points, and with that you can actually do things in parallel much more easily. Because some of these things, they are independent of each other, so you can actually do it in parallel in that sense. So the simple soup would be a workflow like this. While you have the more complicated recipe where you can see that some parts can be done in parallel. So you can buy and chop veggies. Those are independent of heating the water. And also buying the meat is independent of that part. So all these three branches can be done in parallel. I wouldn't put the water on heat when I go out shopping though, but that's another thing. But anyway, so for the concept, this would be a possibility that you can kick off different processes in parallel. This workflow, you had to more or less say that, okay, I'm going to make soup for the military company, and we want to do it for 100 people, so okay, let's make 10 cooks standing chopping veggies. Okay, they can do it parallel too. But, and also same with meat, 10 people chopping meat. That's another way of doing the parallelization. So it depends a little bit on the choice of how you work, how you afterwards do this processing. And for that kind of work, we also have something called DAGs, directed acyclical graphs, and they are a way that promotes this splitted task processing. And there is a lot of these tools available, so then it's about choosing the right one for your task. For deep learning is another thing where also the DAGs are useful, because here again we can kick off a lot of these sub-chains in the processing, and that can also speed up the work. And these are tools that the DAGs we are going to look at, but doing it with in deep learning, not. So that was the end of today's lecture. So we have looked into some different topics. That first of all, we can probably conclude that science with images is not always an easy task. And the images themselves, of course, can reveal information about the samples, but the question is now to find the strategies, how we can analyze them to get the information we want and also be able to do it efficiently. Next week, I'm going to talk about data sets, and if you have too little data, you can do data augmentation, the need for a ground truth, and the last part, I think I will also talk about data frames, a way how to work with tables within Python. And well, that was all for today. I'm a little bit over time. You can take a little break, and then Daniel will take over and show a little bit how to get started with the exercises. And well, that was all for today.